Okay, so moving on to chapter 5. Discrete probability distributions. So what is the idea here? Well, in chapter 4, we did a lot of analysis of probability, but we were always working under the assumption that each outcome is equally likely, right? When we were talking about poker hands, we assumed that drawing one card is as likely as drawing another card. Or when we were rolling die or flipping coins, 1 through 6 came up equally likely, heads or tails came up equally likely. But what if I had a die where I knew it was unfair, where I knew that 1 came up twice as often as any of the other numbers, or a coin that comes up heads 75% of the time, tails 25%, or a deck of cards where, a certain card was more likely to come up than a certain other card? How can I handle that? I would like to generalize the idea of this classical probability that I built up in chapter 4 so that I can handle situations like that with outcomes that aren't equally likely. And that's the goal of chapter 5. So we have some outcomes. We're going to assume that we can enumerate them. So maybe like rolling a die, 1, 2, 3, 4, 5, 6. This is what we mean when we say discrete, that I could label a first one, a second one, a third one. Not necessarily that there's a natural ordering or that there's a natural way to order them. Even with heads and tails, I could just say, okay, the first outcome is heads and the second one is tails. This is opposed to continuous, something like maybe height, where I can't say like the first height that a person could be is 5'0" or something. Or, if this person's 5'0", the next allowable height would be like 5'7" or something. Well, no, that's not how that would work. That would be a continuous variable. That in between any two height measurements, there's another valid height measurement. So this is the sense in which we mean discrete. We can enumerate all of our possible outcomes. For the vast majority of our discussion, we're going to be dealing with finite numbers of outcomes. Depending on time, I might or might not just throw in a little comment about the geometric distribution, which has infinite outcomes. So that would be like the number of coin flips until you get a head or something like that, that could be, in theory, as large as you want. Those are possible. It could take you you could flip 1,000,000 tails before you get your first head, something like that. But for this, for essentially all of our discussion, we're going to be thinking of finite, discrete probability distributions. So that means that we can make a list of our outcomes. And we're allowing for the probabilities to not necessarily be equal. So associated with each outcome, I need to give a probability. If I knew that each outcome was equally likely, then I can infer the probability of each outcome from that, right? If I have 6 sides to the die and they each come up equally likely, I know that the probability of each of them is 1/6. But if I'm telling you I have a die and I don't know if it's balanced or not, or if one side comes up more often than the other, I would have to tell you what percentage of the time does 1 come up, what percentage of the time does 2 come up, and so on. So each outcome is associated with its own probability. So this is a list of probabilities. If I've listed all of my outcomes along with our associated probabilities, Well, my basic probability rules tells me that the sum of the probabilities of all the outcomes in the sample space have to be 1. I also am going to think about my outcomes as being numerical. So if I'm talking about rolling a die, 1, 2, 3, 4, 5, 6, okay, those are already numbers. I'm talking about flipping a coin. I wouldn't want to say my outcome is heads or tails. That's just going to lead to some problems later on. But I might just define my outcome as something like the number of heads on one flip of a coin. So flipping a coin and getting a heads would result in an outcome of 1, because I got 1 head on one flip of the coin. And flipping a coin and getting tails would give an outcome of 0. So I can pretty easily take qualitative information for my experiment and translate it into something quantitative or numerical for my outcomes. So this is what I want for a probability distribution. My outcomes probably ought to be numerical, or at least kind of converted into some numerical sense. The sum has to be equal to 1, sum of the probabilities, and each individual probability has to be between 0 and 1 inclusive. So each of these numbers individually in this right-hand column has to be non-negative and less than or equal to 1. If any of them have probability 1, that's a pretty boring distribution, because that's the only outcome that we can get from that probability experiment. So let's take as an example a coin flip. And let's say that we bet $1 on heads and that it's a fair coin. So what are our outcomes and our probabilities? Let's let X be the amount that we won. So if the flip ends up being a heads, I bet $1 on heads. Then X is positive 1. And if the flip ends up being tails, the amount that I won, well, if I bet $1 on heads and it comes up tails, I lose $1. X is negative 1. So I see I have 2 numerical outcomes now. And associated probabilities, 1/2 and 1/2, or 0.5, 0.5. Doesn't much matter whether we write them as a fraction or decimal. So you might say, well, couldn't we just have evaluated this using chapter 4? Well, sure, we could have. But what can I do now? I could say, what if I had a different scenario where I bet $1 on heads and it's an unfair coin? My outcomes are still the same. But let's say it's an unfair coin. Heads comes up 70% of the time, tails comes up 30% of the time. Well, now I can handle this situation, right? Before I had a little bit of a problem handling the situation, but now I can. Heads comes up 70% of the time, which means I get an outcome of X equals +1 70% of the time. And therefore an outcome of X equals -1, I lose $1 30% of the time. How can I kind of think about this? I could kind of think about this in terms of my chapter 4 information, or chapter 4 structures, by imagining that I have kind of a bag from which I'm going to draw heads or tails. And in chapter 4, I had, one slip of paper in here that said heads, one slip that had tails, and that's the end of the story. I reach in, I draw one, and I get heads or I get tails, 2 outcomes in my sample space. That's all there is to it. But here, maybe I say something like, well, maybe I have 7 slips of paper in here that are heads, and 3 that are tails. So each one of these slips is equally likely to be drawn, but I have like, a slip of paper that has tails on the front and like the number 1 on the back. That's the first tails. Another piece of paper that has tails on the front and 2 on the back. Another piece that has tails on the front, 3 on the back. And similarly with the head. So these are distinct pieces of paper. I'm going to reach in, draw one. I'm going to either heads or tails. And these different slips of paper, these different, outcomes are kind of apportioned unevenly between heads and tails. So that's kind of the generalization of the model, right? It's a little hard to, we're kind of bending over backwards to like force this into the chapter 4 model, which is why we want to use this generalization. We want to think about this in terms of discrete probability distributions and generalizing this idea so that we don't have to try to set up a structure that's kind of like this, where we're like really forcing this into the mold of equally likely outcomes when really we have outcomes that are not equally likely. But we can kind of think of it that way, even though it's, I think, a lot more tedious to do so. So what are we kind of interested in? What were we interested in chapter 3 about knowing about things? Well, we might be interested in knowing kind of what the typical result is. If I play this game, what kind of on average happens? Or another way of saying that is, if I were to play this game 10,000 times and average out my winnings, what do I think the average, say, winning per game would be? What would be the average of X for each game? Or maybe what's the risk? What's the volatility? Do I think that most of the time I'm going to be close to that average, or do I think that quite often I'm going to be far away from it? So the analogous idea for the average or the mean in chapter 5 is called the expected value. We'll see that this is a little bit of a misleading name for this. You might think expected value, okay, maybe that expected value is just going to be +1 because that is the thing that comes up most often. That's not what it means. So the expected value is effectively the center of mass. If we imagined having a chunk of real line with 2 locations, -1 and +1, and a mass of that weighing 0.7 located at +1, a mass weighing 0.3 units, 0.3 grams or whatever at -1, the expected value is the center of mass. It's the balance point where if I put a fulcrum, the distance away from that fulcrum times the mass on one side balances the distance times the mass on the other side. So this is literally a center of mass in this context. We often refer to the expected value as mu, but a lot of times we want to be more explicit about exactly what we're saying. So we use the expected value operator, kind of like the probability operator, similar idea. We're computing the expected value of a random variable. In this case, it's X, so expected value of X. And we could put parentheses around it, if you put parentheses around it, it's not the end of the world. A lot of authors do. For some reason, historically, expected value typically gets square brackets. If you want to use parentheses, it's not the end of the world. I've looked into this. I can't find any good reason why this happens. You know, the only argument that I've been able to really find that makes a little bit of sense is that there are certain mathematical structures in kind of general math, not necessarily in stats or probability, where you use brackets, and that's kind of the situation that we're in here. But that's also not really, it's not consistent. Like when we talk about the variance, it gets parentheses, it doesn't get brackets. Like expected value is the only one of these things that gets brackets. So it's just kind of an interesting little nuance. I'll write it with brackets, but if you wanted to use parentheses, not the end of the world. And it's the expected value is x1 times probability of x1 plus x2 times probability of x2 plus xn times probability of xn. I multiply the outcomes times the probabilities and add them together. This is why our outcomes need to be numerical, because I want to be able to do this. If I had x1 was heads and x2 is tails, I can't multiply heads times 0.7 plus tails times 0.3. That doesn't make sense to do. But I can multiply plus 1 times 0.7 and minus 1 times 0.3. That makes sense to do. Note that this is really a weighted average. Implicitly, we're kind of dividing by the sum of the probabilities. But recall that the sum of our probabilities was 1. So implicitly, we're taking a weighted average, dividing by the probabilities, but this denominator is just always equal to 1, so we just don't write it. So this is a weighted average of the outcomes weighted by the probabilities. And in this kind of a context, it is the center of mass of this setup, where the outcomes represent locations along the real line, and the probabilities represent point masses at those locations, finding the center of mass, finding the balance point of that. So let's compute the expected value for our two distributions up here, the fair coin and then the unfair coin. So what I want to do, I want to multiply the outcomes times the probabilities and then add them together. The way that I like to do this is to just use a chart just like we did in chapter 3. Let me append a column onto the chart. So in black here, I have my probability distribution, but I'm just kind of, kind of stealing it to use it for my calculations. I want to multiply my outcomes times the probabilities and put that answer in this column. Plus 1 times 0.5 is plus 0.5. Minus 1 times 0.5 is minus 0.5. Then I want to add those together. Plus 0.5 minus 0.5 is 0. My expected value is 0 here. My expected amount 1 per game is 0. Again, this is a little bit of, calling this unexpected value is a little bit of a misnomer, because if I bet $1 on heads on a given play, I either win $1 or I lose $1. I never break even. I cannot play this game one time and end up with an outcome of 0 where I don't make or lose any money. What's the sense in which this is true? This is true in the frequentist sense from chapter 4, in the classical probability sense, in the sense that if I imagine playing this game 100 times, 1,000 times, 100,000 times, adding up all my wins and losses and dividing by the number of games I played, I would expect that number to be quite close to 0. So the long run average, or the X bar for a large sample size coming from this process, should be close to 0. Now, what if I had my unfair coin? So again, I'll just kind of steal this probability distribution and build a little bit off to the side of it. I want to multiply my outcomes by my probabilities, then add them together. So I have plus 0.7 minus 0.3. My expected value is plus 0.4. Again, in no game, in no individual game, am I going to win 40 cents on that game. What do I mean in the sense of an expected value or a typical outcome of the game? What I mean is that if I played this game with this unfair coin a whole bunch of times, on average, I would expect to win 40 cents per game. Sometimes I'd win $1 in a game, sometimes I'd lose $1, but since I win $1 more often than I lose $1, it kind of nets out to about 40 cents per game when averaged over a large number of games. So that's the sense in which I mean expected value. It can be very confusing because you think expected value, your natural inclination is to think, well, that's the outcome that I would expect on one play of the game. But keep in mind, with this classical probability, we're always really thinking about this context of if I played this game or performed this experiment, tens of thousands of times, and then kind of averaged together the results or somehow aggregated the results, what would I expect? That's also what I mean by probability, right? If I flip this coin 10,000 times, I'd expect that about 70% of those flips would come up heads and about 30% would come up tails. So we discussed this in chapter 4, but the same idea is applied here in chapter 5. Okay, we've got about 15 minutes left. I think I want to introduce the idea of standard deviation, and we'll probably do standard deviation for one of these. And then we'll come back next time and we'll do several more examples for both expected value and standard deviation. So we know from chapter 3 that the standard deviation is kind of what's the spread of the outcomes? How extreme can one run of this experiment kind of realistically be? So the standard deviation is, well, let's say the variance. Remember, this was something like the average squared deviation from the mean. So I know what the mean is. It's the expected value of x, but for right now, I'm just going to call it mu. I know how to find a deviation from the mean. I can take each outcome and subtract the mean from it, and then I can square that. What's the notion of average here? It's the notion of the weighted average, the expected value up here. So I have a lot of moving pieces, but one thing that I see is that I'm trying to take the average of stuff over here. I want to take the expected value of something that's not just like expected value of X. So let's take an aside. And say, okay, expected value of X is this. So that's coming from that distribution. What's the expected value of some function of X? Well, maybe we could look at, say, expected value of AX plus B. What do I mean by this? Well, what I mean here is that I want to take each outcome, multiply it by a constant A, and then add B. Now I've just transformed this first column here. That didn't actually affect any probabilities, right? These probabilities are the same. I've just transformed the first column. Really, all that I've done is I've changed each outcome from, say, x1 to ax1 plus b, or x2 to ax2 plus b, and so on down to xn turning into axn plus b. So the expected value of a function of x, we just apply that function to each outcome. It's very important that we don't apply that function to the probabilities, though. If I apply a function to the probabilities, it's quite likely that they're not going to any longer add up to 1. I want the probabilities to stay the same, but the outcomes are the ones that get transformed. So that's quite important. So this is one idea that I see here. I also note that from this expected value of ax plus b, I can break apart my sums. I can distribute the probabilities into ax1 probability of x1 plus b probability of x1, or I could collect those ax's that takes care of the first term in each of these parentheses. And then I have all these b bits. So this is what the expected value of ax plus b turns out to be. Let me leapfrog this next line. Need a little more room here. I see here, I can factor A out of everything. And here I can factor B out. What's multiplying B is the sum of all the probabilities, but that's just equal to 1. What's multiplying A is the sum of all of the outcomes times probabilities. That's expected value of X. That A times expected value of X plus B times 1, or I see that the expected value operator is what we call linear. It splits sums apart and constants can come out. Constant multiples can come out of the expected value. So this will also be an important property that we'll use. So the expected value of a function of X, we just apply that function to each of the outcomes, and very importantly, leave the probabilities alone. We need the probabilities to always still add up to 1. We don't want to transform the probabilities, just the outcomes. And we also note that the expected value of constant times X plus constant, the constant addition on the inside just gets added on the outside. The constant multiple against X on the inside can pass through the expected value and become a constant multiple of the expected value. It can multiply on the outside. So what's our standard deviation then? Well, really the variance. What is our variance? Variance of X, or sigma squared, is my mean is mu. I want to find the deviation from the mean, X minus mu. I want to square that. So the transformation that I want to apply to each outcome is subtract the mean and then square. And I want to compute the expected value of that. Just like in chapter 3, the computation for the variance is a bit involved, but it is just a process, right? Once we do it 10 times or something, then it's kind of like, okay, you just turn the crank, you do the steps. We're going to build out this table with a couple other columns to help us compute the variance. And we just kind of turn the crank, we go through the table, we get an answer, and that's that. Okay, so we didn't quite get to, so that's the variance. And then of course, the standard deviation of X is the square root of the variance. So we didn't quite get to an example, and I don't think we're going to have time in the last 4 minutes or so to work through an example. We'll do an example of this next time, but this is the definition for the variance and the standard deviation, completely in line with our ideas from chapter 3, but just applied to this new context where when we talk about the average, we're talking about the weighted average, this expected value operation. So just a super quick recap, because this idea of probability distributions is going to be quite important for the next, for chapter 5, also for chapter 6, which is going to build right off of chapter 5. And in chapter 6, we'll see the central limit theorem, and that's really going to be used all throughout chapters 7 and 8 and much of the rest of the course. So this is really foundational stuff. So let's just kind of quickly review what we talked about last time. So we moved into chapter 5, discrete probability distributions, and we said the idea was chapter 4 was super nice. I mean, we had this nice way of calculating probabilities and so on, number of outcomes in the event over number of outcomes in the sample space, but it had this huge caveat that the outcomes needed to be equally likely. And, you know, sometimes like say a roll of a die, 1 through 6, if it's a fair die, sometimes the outcomes are that you kind of naturally want to think about naturally turn out to be equally likely, and that's pretty nice. Sometimes if you have, say, a couple of die rolls, you have to think about it maybe a specific way, like the sequence of results from, say, 3 die rolls to construct a sample space where the outcomes are equally likely. But if you think a little bit, you can kind of construct such a sample space without too much difficulty. And then there are situations where you'd really have to do some mental gymnastics and really bend over backwards to try to construct, in a sense, a sample space where the outcomes are equally likely. And this is an example of that. What if we were rolling a die and it was an unfair die? So maybe it still has 6 faces, but maybe this die isn't a perfect cube. Maybe the weighting, the density of the material is different throughout the die or something. And for whatever reason, 1 and 2 each come up 10% of the time, but 3 comes up 20% of the time, 4, 25%, 5 and 6 come up 20% and 15% of the time, respectively. We could describe a process this way. I mean, this is a perfectly reasonable way to describe a probability experiment or a population, and another way of thinking about it. But this doesn't really lend itself to the chapter 4 ideas because these aren't equally likely outcomes. I suppose we kind of could force it into the mode of equally likely outcomes if we pretended there were like 100 slips of paper and I'm going to write the number 1 on 10 of them and the number 2 on another 10 and the number 3 on 20 of them. But again, that's a lot of mental gymnastics to really think about something like that every time that we want to compute a probability. So we like to generalize the ideas from chapter 4 to be able to more directly handle these ideas related to probability distributions. There were a couple criteria for a grid like this to be considered a probability distribution. Our outcomes should be quantitative. And really, the reason for this is that we really want to say, what's the mean, what's the standard deviation, things like that. I suppose it wouldn't be the end of the world if our outcomes were qualitative. We just really couldn't do very much with this distribution then, right? We couldn't even really impose an ordering or a ranking on it. So, that would be a perfectly fine, frequency distribution or a fine way to kind of describe that population, I suppose. But really, much of the power of probability distributions would be lost, I think. The other thing is that the sum of the probabilities, so if we add up all of these numbers, should be 1. So if I add up 0.1 plus 0.1 plus 0.2 plus 0.2, that's what, 0.6. And then 0.25 and 0.15 is 0.4. Add those together and we get exactly 1. And this relates back to the idea that the probability of the whole sample space should be 1 from the chapter 4 ideas. And we also see that, things like complementary events are going to come into play here. So what's the probability of rolling a 6? Well, that's 1 minus the probability of rolling a number from 1 to 5 inclusive, things like that, right? So these kinds of rules from chapter 4 do port over to chapter 5 nicely. But we can see, for instance, that the probability of rolling a 3 is not 1/6, just because there are 6 possible outcomes, 1 through 6, because in this case, we don't have equally likely outcomes. So we're assigning a probability to each possible outcome. And the other thing is that outcomes must be quantitative, but for chapter 5, in particular, they must be discrete quantitative. So I should be able to say, what's the first outcome, what's the next outcome, what's the next outcome after that, right? I can label these 1, that's the first one, what's the next one is 2, the next one is 3. That's as opposed to something like, let's say, a person's height, where you could say, well, what's the lowest outcome? Well, I'm not really sure. But even if we said, okay, the lowest outcome, I suppose, could be 0. Maybe we could say that a person can't have negative height. But what's the next outcome, right? If somebody's 5 foot 0 inches tall exactly, what's the next possible outcome? Well, there's not a next possible. Anything that you pick that's above 5 foot 0, any other height that's a possible outcome, say 5 foot 1 inch, there's another possible outcome in between those two, right? Remember, that was the idea that distinguish between discrete versus continuous quantitative. Remember all of that stuff in chapter 1 that we talked about, all of those different types of variables and types of data. And I said that, you know, as we go on through the course, we'll see them pop up and we'll see how they're actually applied to models and modeling techniques. And that's where what we're seeing here. And then, of course, you know, each individual probability has to be in 0 to 1 inclusive. So each of these numbers P of X has to be between 0 and 1. I suppose it could be 0. That would be kind of funny to put in an outcome that has 0 probability, but I guess that doesn't really break anything. Or it could be 1, and if you kind of make the probability 1, then all of the other probabilities are 0, so that's kind of a boring distribution. So most of the time, our probabilities are going to be strictly between 0 and 1, but I suppose it doesn't particularly break anything to make one of the probabilities 0 or 1. So those were the important ideas. Those are the important criteria for whether a chart like this can be considered a probability distribution, a discrete probability distribution. And as I kind of mentioned here, an important fallacy, an important statement that is not always true, is a statement like, if there are X number of possible outcomes, then the chance of a given outcome is always 1 over X. And we can see the absurdity of this just by thinking of an edge case, right? This is something that mathematicians like to do a lot, is say, if you make a claim and you say, I think this is true, it's like, well, can I go out to outer space and kind of disprove it, right? Can I find a counterexample? Well, just think of the lottery, right? You can say, well, there's only 2 possible outcomes, so I either win the Powerball jackpot or I don't win the Powerball jackpot. That's 2 possible outcomes to make up a whole sample space, right? Do you really think that it's a 50-50 chance that I win the Powerball jackpot? If that was true, I'd play the Powerball all the time, and I don't play it. So I don't think if I play this week and I play next week, one of the 2 times I'm probably going to win the whatever it is, $1 billion or something now. Right. So if we look for a way to disprove that, if we think scientifically, like the scientific method, and we say, here's a hypothesis, 2 possible outcomes means the chance is always 50-50, look for a way to disprove it. Don't look for evidence in support of your opinion, look for evidence to try to refute it. And you can pretty quickly think of examples that will refute that. So that Powerball example is like, you know, if X was your winnings are like $1 billion, but like 1 over a couple hundred million is the probability of winning that. Or, you know, your winnings in terms of just say the Powerball winning is 0, like basically the rest of the time, you know, say 119,999,000, a bunch of 9s out of like 120 million or something like that. Okay, so we said a couple of examples of flipping an unfair coin. If I flip a coin and I assign my outcomes to be heads or tails, well, the problem is that that's not really discrete quantitative, right? That's kind of qualitative. But how can I get a quantitative variable out of that? Well, I could just say the number of heads that I get on one flip of a coin. So I've got to be just a little bit careful when I set up my probability distribution to make sure that my outcomes are actually discrete quantitative. And if I count the number of heads I get on one flip of this coin, that is discrete quantitative. If I just said like heads or tails, that's qualitative. So I either get 0 heads on one flip or I get 1 heads on one flip of the coin. And if my unfair coin comes up heads 70% of the time, then X, my random variable, is 0 30% of the time and 1 70% of the time. Or I could think of, say, playing a game where I make a bet against my friend and I bet $1 on this unfair coin and I bet on heads. And I could, you know, think of X being a random variable, say the winnings that I receive. If it comes up tails, then I lose $1 and it comes up tails 30% of the time. If it comes up heads, I win $1 and it comes up heads 70% of the time. So that might be another example where we could convert something that, starts out as kind of qualitative into something quantitative. We have to be very careful to read the problem carefully and decide what is our variable. What are we actually looking to measure here? Is it something like number of heads on one flip? Is it something like amount we win on some game, right? What are we looking to measure? So I don't want to just jump right down here and say heads, like put an H and a T in these two slots. I want to think about, what am I measuring? So what is the expected value? It is the weighted average of the distribution. It's the outcomes weighted by their probabilities. We mentioned that the weighted mean, we have to divide by the sum of the weights, but because the probabilities in total sum to 1, that divisor is just 1, so we don't have to write it. We mentioned that this represents a center of mass. We talked a little more about that last time, so I won't go more into detail on that. Let me expand this a little bit so it's not doing that. There we go. And then we talked about computing an expected value. And I think we computed an expected value or two, introduced the idea of the variance and standard deviation, and kind of left it more or less there. So I think that was a pretty good recap of what we did last time. And then we computed a couple of expected values. So we said, let's consider our number of heads on one flip of an unfair coin from up above, where heads comes up 70% of the time. So we get 0 heads on one flip 30% of the time, and we get 1 heads on one flip 70% of the time. Now, if I want to compute the expected value, I note that the first thing I want to do is I want to multiply each outcome by its probability, and then I want to add those together. So we'll just take our probability distribution, which is the 2 black columns here, and then we'll just kind of build off of that. We'll just append a new column onto the end. That'll be the product of each outcome times its probability. So 0 times 0.3 is 0, and 1 times 0.7 is 0.7. And then the expected value of x, which, remember, we write with these square brackets, and I'm not 100% sure why, but I think it's more of just the historical notation. Our expected value of x is 0.7, and this would be something like, say, heads per flip, something like that. And we also just label this mu. And we mentioned, when we say expected value, what do we mean by that? It's a little bit of a misnomer, maybe. It might lead you to think that, the expected value is the most common result, or the one that you most expect to, the result or the outcome that you most expect to end up with on a given probability experiment. But that's not exactly what it is. It's more the idea from classical probability that if we were to hypothetically repeat this experiment, say 100,000 times, and then average, take X bar for each of those, for the data set consisting where each data point is one of those outcomes, one of those results, then we'd expected that average, that X bar, will be close to this number 0.7. So this is kind of an average across many repeated runs of this probability experiment. So a similar example, what if we instead bet $1 on this unfair coin where probability of heads is 0.7, and we had this distribution from up above? What's the expected value here? So I lose $1 30% of the time. Multiplying those two gives me negative 0.3. And I win $1 70% of the time. Multiplying those two gives me plus 0.7. Oh, so my expected winnings, which I should write as the expected value of x, is negative 0.3 plus 0.7 is plus 0.4. And again, we would call this mu. Now we might ask, what are our units for expected value? Are they some kind of crazy units? Do I need to do something like I did with the variance to standard deviation calculation or something? Well, if I think through this, my units of X are in dollars. Probability of X, well, that's just a number. It doesn't have any units. The product of X and probability of X is in units of dollars. And the expected value of X just sums those together. So my units of expected value are the same units as my original data. So I can think of this as something like, as meaning something like on average, I win 40 cents per play of this game. Now, of course, on any given play, I either lose $1 or I win $1. But because I win $1 a bit more often than I lose $1, if I average this over 100, 1,000, 10,000 games, I'd expect that on average, I would win something close to 40 cents per play. Because the amount of times that I win $1 will outweigh the amount of times that I lose $1. But of course, if I play one time, I'm never going to win exactly $0.4. So an interesting question might be something like, well, there's two ways to make a game fair, so to speak. So that kind of on average in the long run, neither player has an advantage. Typically if one player has an advantage, the other player doesn't really want to play the game. So although that's somehow not true of casinos, I don't exactly understand that. I think that has more to do with psychology than probability. But quite often, if we think that we're at a disadvantage, we're going to be less inclined to play the game. So one way that I could make this game fair would be, of course, just to adjust these probabilities to 50-50, right? I think we can pretty easily see that if we were flipping a fair coin and we were betting, winning or losing the same amount of money, whether it comes up heads or tails, I think we can see that that would be a fair coin. If you want to, you can run through the calculation and make sure that the expected value turns out to be 0, so that the long run average winnings for, say, the player who's betting on heads will be 0. So they don't have really a long-term advantage one way or the other. But maybe the other way that we could do it, if we, for some reason, we're stuck on a desert island and only have this one unfair coin, and for some reason we decide to spend a bunch of time flipping a coin and betting dollars or coconuts or whatever we have on the island. Maybe the other way that we could do this is we could say, well, let me just adjust the payout. So I see that there are kind of two components to this center of mass, right? Or two components to this lever, where I have my outcomes representing position. So I did end up having to draw the lever again, but my outcomes represent position and my probabilities represent mass at that position. If my outcomes are equidistant and my probabilities are equal to 50-50, then we see we balance, of course, right? That would be the betting $1 against $1 on a fair coin. If one of my probabilities is larger than the other one, well, then this starts to slant to the right. But what could I do? Well, maybe I could shoot this one further out, right? If I put this smaller mass further out so that it has a longer moment arm, then that, I think we kind of intuitively see that that's going to balance out, right? So that's what we're saying here. We're saying, okay, where do I need to locate this mass of 0.3 on that beam to make the average turn out to be 0? So if you want to think of it the physics way, I personally like that explanation. I think it's a little more intuitive than the very abstract idea of all these probabilities floating around. But if you're not, some people hate physics. So if you don't like physics, then then that's perfectly fine. But I say, okay, let's say that my friend doesn't want to play my game because they know that my coin is unfair and they don't want to bet $1 against $1. So I say, okay, how much do I have to pay you when I win? Or how much do I have to pay you when you win versus you paying me $1 when I win, to kind of compensate for that unfairness of the coin. So in other words, I'll win more often, but when I win, I'll win less money than you do. You'll win less often, but when you win, you'll win more money per play. So let's say that my opponent will win D dollars whenever the coin comes up tails, and I'll win $1 when it comes up heads. So what's my expected value in terms of D? Well, that's negative 0.3D plus 0.7. And I want to set this equal to 0. That way, neither of us has a long-term advantage over the other. And I see that, what do I get? I get 0.3D equals 0.7, D equals 7/3 is about $2.33. So for this coin that comes up head 70% of the time, tails 30% of the time, the person who takes tails would have to be paid $2.33 or so when they win versus $1 when the person who takes heads wins, to compensate for the unfairness of the coin. And then that would give a fair game. So we would call this a fair game. So neither side has a long-term advantage over the other. Now, of course, on any one play of the game, somebody's either going to win $1 or win $2.33. But what we're saying is, again, if we played this game under these rules 10,000 times and each of us averaged our winnings, we'd expect to come very close to $0 for that average. And we could go back and look at our unfair die example that had 1 through 6 coming up with these probabilities not equally likely. And we could find the expected value. So on average, what number comes up when I say roll a die, roll this die a whole bunch of times and average the results over a whole bunch of rolls. And the expected value is the sum of that column. Oh, I forgot to close down my email. Let me just close that really quickly here. Okay. I don't want it to be dinging throughout the whole class. And here, let's go to the calculator for this. So I've already multiplied each of the first two columns together, and now I just need to add 0.1 plus 0.2 plus my pluses. Oh, there we go. Plus 0.2 plus 0.6 plus 1 plus 1 plus 0.9. Okay, that looks right. And that gives me 3.8. Now, if I had a die where all of the faces were equally likely, if I had a fair die where everything came up 1/6, by the symmetry, I would think that the expected value is going to be 3.5. So for a fair die where all faces are equally likely, I'd expect the expected value is 3.5, and that's just the symmetry argument, right? That's the number that's right between 1 and 6. Be a little careful. It's tempting to think that kind of the average between 1 and 6 is 3, but that would be kind of what we get if we started at 0 up to 6. So if we had like a 7-sided die, I don't know how the geometry would work for that, but we could imagine it. If we had a 7-sided die with all faces equally likely, then the average would be 3. Because 0, 1, 2, 3 or sorry, 1, 2, 3, 4, 5, 6, 7. The average would be 4 then. So I'd need 0 through 6, 7 sides. But anyway, just be careful to realize that the midpoint between 1 and 6 is actually 3.5. It's right between 3 and 4. And if you want to, this would be a good exercise to actually change all of these probabilities to 1/6, keep everything in terms of fractions, and then show that the average does turn out to be, the expected value does turn out to be 3.5 for a fair die. So that would be a good practice exercise when you're rewriting your notes or something. Just try to show that. We can make the argument with the symmetry argument, but we could also make the argument going through the details. Any questions on anything so far? So moving on to variance and standard deviation. And again, we introduced this idea last time, but I have a couple other things that I want to mention here. So similar to chapter 3, the variance is the average squared deviation from the mean. So each outcome has a deviation from the mean. We can square that deviation and then take the expected value of that. It turns out we can also write this a different way. We can write it as expected value of x squared minus mu squared. And then the standard deviation, as always, is just the square root of the variance. So some side notes. We talked about a couple of these last time. We didn't talk about all of them, though, I don't think. So the first is that the expected value of a function of x, when I say something like expected value of x squared, or expected value of x minus mu all squared, what do I mean by that? What I mean is apply that function to the outcomes, but very importantly, do not apply it to the probabilities. If I go messing around with these probabilities, it's almost certain that they're not going to sum to 1 anymore, right? So I can't apply the function to the probabilities pretty clearly because they still have to sum to 1. The only thing that gets the function applied to it is the outcomes. The probabilities stay the same as the original distribution. So for example, expected value of x squared is the first outcome squared times the probability of the first outcome. The probability does not get squared, and so on down the line. We did talk about the expected value being linear, and we showed that. Here's the argument for that. In other words, expected value of constant times x plus constant equals constant times expected value of x plus constant. So the expected value splits sums apart, and constants can come out of it. Constant multiples can come out of it. So that's going to be a super nice property for expected value. Now let's see how we get from here to here. Those are two different ways of computing the variance. How do we get from one to the other? The expected value of, oh, and I just realized I have a typo down here. Let me fix that before I forget. That should be a squared. Let me check really quick. Did I make that mistake anywhere else? I don't think so. Okay, yeah, that was the only place I had that. Okay, so the expected value of x minus mu squared. Well, if I think of x minus mu squared, this is x minus mu times x minus mu. And I can multiply this out by FOIL, right? First, outer, inner, last. My firsts are x squared. My outers are minus mu x. My inners are minus mu x. And my last gives me plus, because the two minuses make a plus, mu squared. So this is the expected value of x squared minus 2 mu x plus mu squared. I know that expected value splits sums apart. So this is expected value of x squared plus expected value of negative 2 mu x plus, well, the expected value of mu squared. Well, the expected value of a constant is just a constant. We really saw that here, right? If you imagine a is 0, expected value of b equals b. In other words, if I was playing a game, it's kind of a boring game, but if I was playing a game where I only had one outcome, and that was what I got literally every time I played the game, if I won $1 exactly every time I played the game, what would my average winnings per game be over 100,000 games? $1, of course, right? So expected value of mu squared is just a constant. So expected value of mu squared is just mu squared. I note that my negative 2 mu can come out, again, imagining b was 0 and a is negative 2 mu, that constant, that a comes out, and I have no b to speak of in that case. But this is negative 2 mu times expected value of x, but expected value of x is just another name for mu. So this is expected value of x squared minus 2 mu squared plus mu squared. That's expected value of x squared minus mu squared. That's the variance of x. So two ways to write the variance of x. We could also write this using expected value of x instead of mu. And something very important to note is pretty clearly the variance is not just always 0. That would be quite a boring measure, right? In other words, this difference is not always 0. These two things aren't the same thing. Expected value of x squared is not just the square of the mean. The power on x does not come out of the expected value. Constant multiples and constant sums can come out of expected values, but powers cannot be pulled through expected values. So that's an important little detail here. And I think it's good to know both ways of doing this computation. So when you're doing the homework, do a couple of them one way, a couple of the other way. I don't personally think that there's a huge benefit to one or the other way. So you can, kind of pick the way that you like best. But this way is a little more intuitive for where it comes from. The expected squared deviation from the mean sounds a lot like what we had in chapter 3. And this one can sometimes simplify the calculations. I think it's sometimes a little simpler to do it this way. Just makes the numbers sometimes turn out a little nicer, but it's not, I don't think it's a huge difference. Okay, so let's revisit our number of heads on one flip of an unfair coin. Heads coming up 70% of the time. We saw that our expected value, or mu, was 0.7. So let's just go through and compute two more columns here. I'm trying to select just these two columns. That's not working. There we go. Let's try to compute these two columns. So I've computed my blue column already. I needed that to find mu. And then these red columns are the ones that I'm going to use to find variance and standard deviation. So for variance, I need the expected value of x minus mu squared. In other words, I need to compute the updated outcome, in a sense, x minus mu squared. And then I need to multiply that by the probability and then add them together. That's how I did an expected value. I took my outcome times my probability, added them together. So expected value of x minus mu squared, I just have to adjust my outcomes to be x minus mu squared. So what is this x minus that mu squared? That's 0.3 squared is 0.09. Should have left myself a little more room here. And then this outcome 1 minus 0.7 all squared. Oh, I jumped ahead, didn't I? The next line is the 0.3 squared. Let me just erase that. Sorry about that. 0 minus 0.7 is, of course, negative 0.7. Squared is, let me just expand this because I'm trying to squeeze everything into this little tiny spot. So negative 0.7 squared is positive 0.49. And 1 minus 0.7 is positive 0.3 squared is 0.09. Now, if I multiply x minus b squared by its probability, 0.49 times 0.3, let's figure out what that is. Computer's being very laggy today. Both OneNote and the calculator don't really want to keep up. So that's 0.147. And then 0.09 times its probability, 0.7. Is 0.063. And then to get my variance, I just add those together. So what's this going to be? Well, 14 plus 6 is so that gives me 0.2. And I think that's going to be 0.21. Let's just double check that. So if I have 0.063 plus 0.147. So my variance here is 0.21, and my standard deviation is going to be the square root of that. So second square root of second negative sign puts in the previous answer. And that gives me about 0.46. So I see that for this unfair coin where heads comes up 70% of the time, the expected value, the mean is 0.7, basically 0.7 heads per flip on average. And the standard deviation is 0.46 heads per flip. So another approach that we could take, so we could take this approach, that's fine, that's using this first formula directly. Another approach we could take is the second formula, and it has, again, some pros and some cons. Computing expected value of x squared is typically easier than computing this expected value. But then we have to do this extra calculation at the end where we subtract off the square of the mean. So I think all in all, it's, about 6 of one, half dozen of the other, but we'll do a couple examples both ways. So here we're looking at the winnings on a bet of $1 on the unfair coin. So we either win negative $1, we lose $1 30% of the time, win $1 70% of the time. And again, we saw that mu was plus 0.4. And now the thing that we want to compute is expected value of x squared. So I want to take each of my outcomes, square each one, and then take the weighted average. So negative 1 squared is positive 1. And positive 1 squared is positive 1. I want to take each element in this column and multiply it by its associated probability. Again, be very careful. Don't square the probabilities, just square the outcomes. 1 times 0.3 is 0.3. 1 times 0.7 is 0.7. And now the sum here is the expected value of x squared which is 1. And maybe I shouldn't write a box around it. I'll write like a squiggly line. That's expected value of x squared. But don't forget, we still need to subtract off the square of the mean to get the variance. So the variance of x is the expected value of x squared minus the square of the mean. So 1 minus, well, 0.4 squared is 0.16. So that should give me 0.84 for the variance. And then we want to square root that. To get the standard deviation. So the average win per play of the game is 40 cents plus $0.4. And the standard deviation of wins is 0.92. Now let's keep track of our units in both of these examples. So x here is in dollars. X squared is in dollars squared. Probability is a unitless number, so x squared times probability is dollars squared. If I add those together to get expected value of x squared, this is in units of square dollar. So my expected value of x squared is 1 square dollar, which doesn't make a whole lot of sense. My mean is in dollars. So my expected value of x squared is 1 square dollar. The square of the mean is in units of dollars squared as well. I subtract those. My variance, as I would kind of expect from chapter 3, is in dollars squared. And then I square root to get the standard deviation back in dollars. Just as I'd expect from chapter 3, the same kind of ideas are true here in chapter 5. And it doesn't matter which way I calculate it, because I noticed that, let's just pretend that x was in units of dollars. It's just a counting number, so there's no real explicit units here, but let's pretend it was in dollars. Then the mean would be in dollars, and x minus mu squared would be, say, in dollars squared. This column be in dollars squared, and again, my variance would be in square dollars. So a similar thing up here, as soon as I introduce this square, either in that column or that column, that's whenever I get my square units, and at the end I square root to get rid of those square units. Okay, so let's look at the number rolled in an unfair die. Push this down a couple. And here I think I'm going to go with the x squared example, because I'm starting to think, okay, well, for this problem, if I think ahead, I'm going to have a mean that's not a very nice number. And if I try to do 1 minus whatever that was, 3.7 or something, that's not a very nice number. And then I try to square that. I think this is going to work a lot easier if I use x squared for this problem and then compute expected value of x squared. That'll make my chart simpler. And I'm more than happy to do one extra little calculation at the end, because it makes the rest of the chart simpler. So the trade-off in this case is pretty clear. I'd rather do the expected value of x squared minus mu squared. But in a simpler problem, the trade-off might go the other way. So we computed the expected value for this before. I think it was 3.7, 3.8. Okay. So up there we had that the mean was 3.8, right? I definitely don't want to do 1 minus 3.8 is 2.8 and then try to square that and then multiply by a probability. I think it's going to be cleaner to do it this way for this problem. Right? That's one reason it's nice to have flexibility. You can choose between, which tool you want to choose for the job. Sometimes one tool is better than the other. So here, x is 1, so x squared is 1. When x is 2, x squared is 4, 9, 16, 25, and 36. And remember, our goal here is to compute expected value of x squared as our first step to getting this whole piece. So I need to square each outcome and then just multiply by the original probability. So I want to multiply this column against that column and put that in that last column. So 1 times 0.1 is 0.1. 4 times 0.1 is 0.4. 9 times 0.2 is 1.8. 16 times 0.25, well, that's 16 times 1/4. That's just 4. We can write 4.0 if we want. 25 times 0.2, that's 25 times 1/5 is 5. And 36 times 0.15, that might be a bit annoying to do. It's going to be 3.6 plus half of that, but so 5.4. And then the expected value of x squared is just this sum. So I'm going to come back over here and add 5. Did that not go through? Plus, there we go, 5. I want to add 4, 1.8, 0.4, and 0.1. So let me just check that because I was dropping a lot of my keystrokes there. Okay, that looks right. So 16.7 for expected value of x squared. And then what I need to do, I need to subtract off the square of the mean. So the variance of x is the expected value of x squared, 16.7 minus the square of the mean. So I want to take this number, subtract off. Geez, I just can't. 3.8 squared. I think after I finish this problem, I'm going to take a second and just restart a couple of these programs. Sometimes that helps. Okay, so 2.26. And then the standard deviation is just the square root of this number 2.26, square root of the variance, which is about 1.5. So my mean outcome from the roll of this this unfair die is 3.8, and the standard deviation is 1.5. So give me just 1 second here. I don't think we need the calculator anymore, so I'll just close that. Let me close OneNote. It's not like I have anything, crazy open here, but let me just try to get rid of some of my Chrome tabs. Maybe that will help. All right. Yeah, I think it might have been my Chrome tabs that I had open. I had a bunch of things open that I was doing some Blackboard stuff and some WebAssign and my math lab and stuff this morning, just kind of answering student questions and stuff. So I think that might have been just contributing to things. I had all those tabs still open. Okay, so let's look at one last example here. So one thing that is kind of an interesting type of just canonical problem, an interesting type of problem that pops up over and over, is this idea where we have outcomes that are either 0 or 1, with probability of a 1 being p. So we'll actually see in another section or two, sometimes we label this failure or success. So if we're looking for a particular thing, we might succeed in finding it. We might see that thing, or we might not see it. And the likelihood that we see the thing that we're looking for is p. And therefore, the likelihood we don't see it is 1 minus p. So this is called a Bernoulli trial. And let's figure out the mean and variance for this. Well, the mean for a Bernoulli trial is just going to be, it's going to be 0 times 1 minus p is 0. 1 times p is p. The expected value is just 0 plus p, or p. Now, this isn't the exact same p as the probability. This p kind of, in a sense, kind of picks up a unit in a manner of speaking from that x column, but obviously it's the same number as the probability. If I square x, I actually get the same numbers, right? 0 squared is 0, 1 squared is 1. If I compute x squared times probability of x, I get 0 times 1 minus p is 0, 1 times p is p. Expected value of x squared is also p. Be a little careful, we're not at the variance yet. Remember, we have one more step. We have to subtract off the square of the mean. So what's the variance? Well, it's p minus p squared, or it's p times 1 minus p for the variance. And what's our standard deviation? Just the square root of that. So something interesting that we can look at is, well, what is the variance for different values of p? I'm going to use the variance just because we don't have to deal with the square root then. I can imagine p, well, p is a probability, clearly. It has to be between 0 and 1. For certain p's, do I know the variance? Well, sure, when p is 0, the variance is obviously 0. That's clear from the formula. It's also clear from, well, if p is 0, that means I can never get a 1. It means the only thing that can happen is to get a 0. Clearly, there's no variance there, right? Every time I run this experiment, it turns out 0 with no variation whatsoever. Similarly, if p is 1, algebraically, I see I should get a variance of 0. But also logically, I see if p is 1, then 100% of the time, literally every time that I run this experiment, it comes out 1. There's no variation there either. And then I see that this is a quadratic in p, right? It's a quadratic opening down in p. I have an axis of symmetry here at 1/2, p equals 1/2. This gives me a vertex at, what would that be? 1/2 comma 1/4. 1/2 times 1 minus 1/2. This is for variance. And so I actually see that if I'm flipping a coin, so to speak, and I'm counting the number of heads on one flip, something like that, I see that kind of the highest variance I have, the maximal variance that I can get, is from a fair coin. If my coin is biased one way or the other, the variance actually decreases. And this actually is kind of an important concept in statistics. We won't talk a whole lot about it, but a lot of times there are things that you say, oh, I think somebody just pulled that out of thin air or something like that, or why do they use that distribution instead of a different one when modeling things? And actually, a lot of times it comes down to this idea of maximal entropy. In other words, if I was going to flip a coin and I wasn't sure if it was fair or not, what model should I maybe in some circumstances assign to that coin when I actually don't know the underlying distribution? Well, the best model in some senses is to assign probability 1/2 to heads and tails, even if I don't know that it's a fair coin. And essentially, why is that? Well, that gives the highest variance. That's kind of respecting the fact that I don't know much about this system, so I'm allowing for the greatest amount of variation in the system. Or in other words, predictions and things that I make under the assumption of a fair coin, if I had stronger information, those predictions would still hold. But if I assumed a strong piece of information that gave a low variance, and I tried to make predictions on that, that might be kind of a flippant prediction to make. That prediction may end up being very untrue if my original assumption was not valid. So that's kind of the idea that we can see here. So we'll see this very explicitly when we get to things like confidence intervals and hypothesis tests for population proportions. We'll say basically, if we don't have a good idea what the proportion is, we should choose p equals 1/2. And this is why that's kind of like the worst case scenario. That's the most conservative estimate. It's the choice for p that maximizes the variance, that allows for the most conservative estimate. So we know that if we can satisfy our statement for p equals 1/2, if p turns out to be something else, our statement is still satisfied. Either our statement about confidence or our statement about statistical significance, something like that. And this is an important idea that we'll use over and over, is kind of taking this conservative approach so that we know that we can, even in the worst case, still stay true to our statement that we're making about something about the system. Okay, so that ends 5.1. Are there any questions on 5.1? Okay, now I want to take a couple minutes to review some of the theorems we had talked about before and give some proofs as well as a little bit of insight, hopefully. So 2 theorems that we've talked about that are going to be pretty important for some stuff coming down the line is Chebyshev's theorem and the law of large numbers. So these are important ideas for when we want to try to marry the theoretical side of things and the practical side of things. And we'll see that kind of at the end of chapter 6 in the central limit theorem. So we've already done some discussions of properties and so on. I think I actually forgot to mention one property. Yeah, I forgot to mention this. So as an exercise, try to show this property, that the variance of ax plus b is a squared times variance of x, and b doesn't affect it at all. And it does kind of make sense because ax plus b, the b just shifts where it's located. It doesn't change the spread. But so a comes out of the variance as a squared, and the plus b just goes away. That was another important property. But so along with a couple of these properties, we're going to go through some proofs that I think will be helpful for later on in the course. Okay, so the first theorem, Chebyshev's theorem. So let's assume that the mean and the standard deviation are finite and that we have a number k that's bigger than 0. The claim of Chebyshev is that the proportion of data points with value more than k standard deviations away from the mean is at most 1 over k squared. So from the chapter 4 notation, we can say that the probability that, well, what does xi minus mu in absolute values mean? If absolute xi minus mu less than, or sorry, greater than or equal to k sigma, well, that means that the complementary event of this thing being bigger than k sigma is being less than k sigma. So this is the complement going here. Some statement about xi being bigger than or equal to some number. The complement of that is being less than some number. And what does this mean? If the absolute value of something is less than some number, that means the thing itself is either, it was both less than that number and greater than negative that number. So if I tell you that the absolute value of y is less than 3, that means that y has to be between -3 and 3. Okay. Or another way of saying this is that xi is less than mu plus k sigma and bigger than mu minus k sigma. So note that this statement and this statement are equivalent statements. Let's assume, as usual, that x1 through xn are sorted in an increasing manner. Then we can split the data points into 3 classes. Those that fall to the left of mu minus k sigma, those that are at least k sigma below mu. And as an aside, I'm not being super careful about my inequalities being strict or non-strict here. It doesn't really matter that much. So when I say at least, I mean, maybe that conflicts with this being strict, but I'm not being super worried about that. So we can split the data into 3 classes, those with a value at least k sigma below mu, so that are to the left of this left cutoff. Those with a value within k sigma of mu, those that satisfy this blue criterion over here on the right. And those that are at least k sigma above mu, those that are to the right of the right cutoff. Right, so this criterion splits the real line into 3 segments. And these are our 3 classes. Okay, now that we have that set up, let's look at our definition of sigma squared. Sigma squared by definition is 1 over n times the sum. I'm using summation notation here because otherwise it would just be horrendous to try to write all of this out. So 1 over n times the sum of the xi minus mu squareds. So this is just like x1 minus mu squared plus x2 minus mu squared and so on over n. Well, that's bigger than or equal to the 1 over n just copies over. If I replace my sum of xi minus mu squared summing over all of the data points, if I replace that just by the sum of the data points where absolute xi minus mu is bigger than or equal to k sigma, in other words, if I only count the data points in classes 1 and 3, I've removed some data points. I've removed some contributions to this sum. I note that every contribution to the sum is non-negative because it's something squared. So by removing contributions to the sum, that can only make it smaller. So this sum, summing over all of the class 1 and class 3 data points, but not the class 2s, is smaller than the sum that is used in sigma squared, because I've removed some positive or usually positive things that I would be adding here. And then I note that for data points where absolute xi minus mu is bigger than or equal to k sigma, well then xi minus mu squared is bigger than or equal to k squared sigma squared, or k sigma all squared, just by direct use of this property here. So if I replace all of my xi minus mu squareds by k squared sigma squared, or in other words, if I basically just pretend that all of my data points out here were instead located right at that border, and similarly over here, that's going to make this sum even less. We can see that directly algebraically, or we can see that through imagining what's happening to the variance as I start squeezing outliers inward towards the mean. That's going to make my sum here less. But then I noticed that this is just k squared sigma squared over n times what? Times basically the sum of 1, adding 1 to itself, how many times? 1 time for each data point that is more than k sigma away from the mean. Or this just counts the number of data points with value more than k sigma from mu. But the number of data points with value more than k sigma from mu divided by n is the probability that a data point is more than k standard deviations from the mean. So I'm shifting this n down here underneath this number of data points bit, and that's just the probability. If I think of each data point as, if I'm randomly choosing from here, from this data set, if each data point is equally likely to be chosen, then the number of outcomes I have in my sample space is the number of data points that I have in my data set, that's n, and the number of outcomes in the event that I'm interested in, this absolute xi minus mu bigger than or equal to k sigma, being more than k standard deviations from the mean. The number of outcomes in that event is just the number of data points with value more than k standard deviations from the mean. So what do I get? I get that sigma squared, all of my inequalities point in the same direction. That's very important. Sigma squared is greater than or equal to k squared sigma squared times this probability. Sigma squared is always non-negative, and for anything interesting, it's strictly positive, so we're not worried about dividing through by it. So we can divide through by it. It does not change the inequality, and we get that probability of absolute xi minus mu bigger or equal to k sigma is less than, so pointing this direction, and then I can divide through by my k squared to get a 1 over k squared. And remember up here, this was one way of writing Chebyshev's theorem. This is the way we kind of saw it in the book, but looking at the complementary event here just makes it go a little more smoothly for the calculations. So this is a full and formal proof of Chebyshev's theorem. Going to the sample standard deviation actually doesn't cause a problem at all. This n is just replaced by n minus 1, and that doesn't cause a problem. So remember, the important idea of Chebyshev is that the more standard deviations away from the mean that we go, the larger the proportion of data points that has to be within that chunk of the real line. Or as k goes to infinity, the probability that we find a data point that's more than k standard deviations from the mean goes to 0. And I think that kind of intuitively makes sense, but this is the formal proof of it. So what else did we have? Well, we had the law of large numbers. That was another theorem. That was something that we claim to be true, and I really haven't demonstrated to you. So as an aside, when I make statements in this course, as a general rule, ideally, I would like to prove everything carefully to you, and that's often what I try to do. In probability and statistics, in this course, we're focused a little more on application, and some of the proofs of some of the theorems that are really important, like the central limit theorem, are frankly just kind of above the expectations for the course, the background that you would need to know, or how much time we would need to spend, working on this material to get to the point where we could do a proof of central limit theorem would just be really far beyond the scope of this course. So often I try to prove things, and when I can, I'll give you the formal proof. Sometimes with things like central limit theorem, we really can't do the formal proof, but we'll see that we will have proved carefully a couple aspects of the central limit theorem, and then I'll try to give you empirical evidence. I'll try to show you some simulations or something that give evidence in favor of what I'm claiming. So in a pure math course, if this was like, probability and statistics for math majors, we would go through the formal proofs of all of these things. But this is kind of a hybrid course. So sometimes we do proofs, and sometimes we do simulations and experiments to try to demonstrate that a claim is true. But I will, I'll never make a claim, a formal claim, without either giving you proof or evidence or stating that it's an opinion. So there are some things like, I think that a histogram should be set up this way or something. Well, that's clearly an opinion, right? But making a statement like Chebyshev's theorem is a very specific statement, and we should give either proof or empirical evidence in favor of that. So here's the proof. So let's work on proving the law of large numbers. So this is going to be in a couple of parts. So we'll first look at the weak law of large numbers, and what the weak law of large numbers says is that x bar, suppose that we have a sample of size n, we compute x bar for that sample. As the sample size gets larger, as n goes to infinity, as our sample size goes to infinity, the x bar for our sample goes to the population mean. Now, on one hand, you might say to yourself, well, that kind of makes sense, because if the mean is 1 million people, even, like, as n goes to infinity, well, eventually n is going to be 1 million, and don't we just sample the whole population? Well, what we're saying here is that the sample taken with replacement. So in other words, I sample one person from the population, I whatever measure their height, but I put them back in the population, and they could be resampled at a later time. They could be resampled at a future n, or a future I guess, as a future data point. So really what we're saying is that the sample mean converges to the population mean as we take larger and larger samples. So let's assume that the xi's are independent and identically distributed random variables. Essentially, that just means that they kind of come from the same distribution. Let's assume they have finite mean mu and finite variance sigma squared. So we need to show the following, and this might be a little bit hard to understand at first, but we'll kind of walk through what it means. We need to show that for any positive real number, no matter how small you make it, so we'll call it epsilon. That's kind of a typical standard name for a small real number, is the Greek letter epsilon. For any small real number, no matter how small you make it, the probability that the sample mean for a sample of size n minus the population mean in absolute value is bigger than or equal to epsilon. In other words, the probability that the sample mean is more than epsilon, some small number away from the population mean, goes to 0 as sample size goes to infinity. So if we imagine picking an epsilon like 0.1, we want to be able to show that the probability that the sample mean minus the population mean in absolute value, that the absolute difference between sample and population mean, the probability that's bigger than or equal to 0.1 goes to 0 and then goes to infinity. And we want to be able to make that statement whether you chose 0.1 or whether you chose 0.01 or 10 to the minus 10, whatever positive real number you put in here, that could be a difference between the sample mean and population mean. We want to show that the probability that we end up with that much deviation or more between the means goes to 0 as sample size goes to infinity. So what do we do then? Well, we can consider our random variable to be x bar n. Now, what do I mean here by this? This seems kind of strange to say, right? We think if I have a sample of size n, x bar is just like what it is, right? It's not a random variable. If we all had the same, 30 data points in a sample, we'd all compute x bar to be the same. Well, this is what I mean here when I say consider x bar to be a random variable. If we just look at a fixed data set, x bar is fixed. It is what it is. But if I think of the entire process, what did I do? Well, to get that data set, I had to take a sample from the population. If I take a random sample from the population, if I sample, 30 Pittsburghers out of the million or so Pittsburghers, let's say, and I measure their heights, and I get a data set and I compute x bar, from the standpoint of just that data set, my x bar is fixed. But from the standpoint of the whole process, if each of you did that whole process, if each of you went out and randomly chose 30 people, we'd all probably have mostly different people, right? All of our samples would be basically different. So then when I compute x bar, or you compute x bar, or somebody else computes x bar for a sample of size 30, because the random sampling process leads to randomness, leads to different samples, we're going to get different x bars. So that's an important idea here. Sometimes, like in chapter 3, we're just looking from the perspective of, I have a data set in front of me, how do I compute x bar for that data set? But sometimes, like when we're talking more about probabilities, we're looking at a slightly bigger picture. We're saying, well, this data set represents one possible sample from the population, but we could have gotten another sample, and a different sample would have led to a different value of x bar. So we actually realize that the value of x bar that we get through this process is itself a random variable. When I repeat the process different times, the process being taking a sample and then computing x bar, I get different outcomes for x bar. In other words, that probability experiment leads to an x bar, which is described by a random variable. And I say here, note that the mean of x bar n, if this is a random variable, it has a mean and it has a standard deviation, just like random variables we've talked about recently. I claim that its mean is mu. The mean of this random variable x bar is mu. That kind of makes sense. That's like saying that the average of the average is the average. That kind of makes sense. If I repeatedly average something, it seems like that should be pretty stable and not go anywhere. And I claim that the variance of this random variable x bar n is sigma squared over n, where sigma squared is the variance of the population. So I have a random variable x bar from the perspective of taking the random sample, then computing x bar. That random variable has a mean and a variance, and its mean and variance, I claim, are mu and sigma squared over n. Let's make this argument. So what's the expected value of x bar n? Well, x bar for n data points is the sum of the n data points divided by n. I want the expected value of that. But remember that expected value is linear. It can break sums apart and constants can come out. So the 1 over n can come out. And then I just have expected value of x1 plus x2 plus xn. But the expected value can break those sums apart. But I also noticed that the expected value for the first data point, or the expected value for the second, or for the nth data point, that's really just the expected value of X. That's really just the expected value of the population, the mean of the population. So I'm just adding mu together, adding mu to itself, n times here, which gives me n times mu. 1 over n times mu just gives me mu. So that's kind of nice. In other words, what I'm saying is if I take a sample, let's say sample size 30, I compute X bar and I write that number down. And I take another sample, I compute X bar, I write that number down. If I have a list of a whole bunch of different X bars from different samples from the population, if I took that list and averaged it for a whole bunch of different samples, I'd expect that average to be very close to the population mean, mu. And that kind of makes sense. If we actually thought through the algebra, we'd see really what we're doing is just kind of taking an average of bigger and bigger samples. And so that kind of meshes very nicely with the weak law of large numbers. What about our variance? Well, if we try to do the same thing as the variance up here, remember the exercise that I showed you was that constants pop out of variances, but they get squared. The variance just always likes to square stuff, whether it's units or constants coming out or whatever. And then the question is, what's the variance of the sum of random variables? Well, because we assumed independence, we have this terminology now from chapter 4 about independence and so on. Because we assumed independence, in other words, the knowledge of one random variable doesn't affect or doesn't give us any other knowledge about any other random variable, we can split this variance up. And we'll look at this maybe in a little more detail down below here. It's a little messy, so I'm just going to leave that as kind of an aside later on. We can split the variance of the sum into the sum of the variances because of independence. So then what do we have? I have 1 over n squared times, well, the variance of x1 plus the variance of x2 and all the way on out. But the variance of each data point, that's just the variance of one randomly chosen individual from the population. That's just sigma squared. So just like up above, I'm just adding sigma squared to itself n times. Or I have 1 over n squared times n sigma squared. And note that where the n's canceled out here, and I was just left with mu for the expected value, because when I pull this 1 over n through the variance, it gets hit with a square, 1 over n squared and n sigma squared, the only one of the factors of n cancels out, and I'm left with sigma squared over n. So in other words, as n increases, the expected value stays the same. The expected value of the sample mean stays the same at mu, but the variance of the sample mean has an n in the bottom. As n increases, sigma squared over n goes to 0. My variance goes to 0. So if I look at Chebyshev's theorem, recall that this is what it said. For the random variable x bar n, that's what we're calling our random variable, the sample mean for a sample of size n, we can make this claim, right? What did Chebyshev say? The probability that absolute value of random variable minus its mean is bigger than or equal to k times its standard deviation, less than or equal to 1 over k squared. Probability that random variable minus the mean of that random variable, which we showed to be mu, is greater than or equal to k times its standard deviation, which I'm going to call sigma sub x bar. So I'm going to name this sigma x bar squared, just as a notation. So that's what I mean by sigma x bar, the standard deviation associated with this variance. Well, what I really want to show looks a heck of a lot like Chebyshev's statement. In other words, if I make k sigma x bar equal to epsilon, well, then that tells me that k has to be epsilon over sigma x bar for any non-trivial distribution. I'm not dividing by 0, so I'm not worried about that. 1 over k, then I just flip this, sigma x bar over epsilon, and 1 over k squared is sigma x bar squared over epsilon squared. But I know what sigma x bar squared is. That's just sigma squared over n. So I can replace sigma x bar squared with sigma squared over n. And what I see is that epsilon is fixed, sigma is fixed. Sigma is a characteristic of the population, not of our samples. Epsilon is what we chose over here. Well, then the probability that x bar n and mu are more than epsilon different is less than or equal to sigma squared over n epsilon squared, because sigma squared and epsilon squared are fixed and n is in the denominator. This goes to 0 as n gets big. So that's the proof of what's called the weak law of large numbers, that the sample mean goes to the population mean as n goes to infinity. It's a little bit into the nitty-gritty, which is why I kind of left it as an appendix for section 5.1. But I think we can see how a lot of this stuff that we've developed in chapters 4 and 5 is really helpful for talking about some of these theorems. Now, something you might balk at is, well, what I just proved is that the sample mean goes to the population mean as n goes to infinity. That seems kind of like a far cry from the chapter 4 law of large numbers that said something about essentially the whole frequency distribution. That said that the relative frequency distribution obtained from a sample approaches the true probability distribution as n gets larger. That seems like a much stronger and broader statement than just saying that the sample mean goes to the population mean. Well, we actually can get this directly from the weak law of large numbers. We can consider an event E. This is going to be an event that looks kind of like that Bernoulli trial that I mentioned just on the last set of slides, or last OneNote thing, whatever it is. So let's consider an event E where for each xi, for each data point in our data set, clearly either that data point is in the event or that data point is not in the event. It's either in the event or it's in its complement. That's clearly true. So if we're rolling a die or something and our event that we're interested in is probability, or say the event we're interested in is getting a 1, if I roll the die, I either get a 1 or I don't get a 1. Let me consider a new random variable related to that, yi, and let me say that it is 0 if xi is not in the event, and it's 1 if xi is in the event. So if I get a success, if I'm looking for rolling a 1 and somebody rolls a 1 and they get a 1, that's one success, one roll of a 1 on the trial. Or if they roll some other number, that's a 0. So essentially, yi is counting for this one data point. Of that one data point, how many are in the event? It's either not in the event, 0 of them are in the event, or it is in the event, 1 out of 1 data point is in the event. That's what yi looks at. Then the number of xi, the number of these data points that satisfy the event, is just the sum of the y's, right? Each data point that does satisfy the event gets a value 1, and each one that does not gets a value 0 and is essentially skipped over by the sum. So then what's the probability of being in the event under the sample? So for a sample of size n, what's the empirical probability of being in the event? It's the sum of the y's divided by n, right? It's the number of data points that are in the event y1 plus y2, et cetera, through plus yn, divided by the total number of data points, divided by the size of the sample space, which is n. But this is just y bar n, right? This is just the average of the random variable y. And by the weak law of large numbers, this goes to the true probability of the event. This goes to the population mean for y, the population probability that a member of the population is in the event. So we did use something that I haven't proved yet. We used up here that the variance of the sample mean, and remember, we were thinking of the sample mean as really coming from a random process that consists of collecting a sample and then computing X bar. It's the collecting the sample from the population that's the random process. But we said that the variance of the sample mean, we could break the variance of the sum into the sum of the variances. And well, number one, we claimed that we could do that, and I really haven't given you any reason to believe we can do that. And then we said that independence played an important part here. So let's look at why we can break the variance of the sum into the sum of the variances, kind of like we did with expected value. We don't have any reason to believe we should be able to do this. We can even see that with the expected value, the constant just comes out, but in the variance, the constant comes out with the square, right? So we have no reason to initially believe that we ought to be able to do this. So let's look at just the variance of two random variables, say x and y. Variance of x plus y, right? That's essentially what we have up here. We just have the variance of, in this case, we have a bunch of random variables added together, but if we can show that this happens for two random variables, we could extend that to a whole bunch of random variables added together. Okay, so what is the variance of something? It's the expected value of that thing minus the mean of that thing all squared. And it's a little strange to write it this way, right? We have expected value of random variable minus its mean, which we're writing as also expected value of random variable all squared. And we can see that we can rearrange this a little bit. We can have x plus y. We know that expected value of x plus y is expected value of x plus expected value of y. We've shown that before. So that's just mu x plus mu y. And we can rearrange to get this. Expected value of x minus mu x plus y minus mu y all squared. We also know that we have a first thing plus a second thing squared. We can FOIL that binomial. We can multiply that binomial out to get first thing squared. If I can select this, plus second thing squared, plus twice the product of the cross terms, plus twice this times this. And we note that we have variance of x plus variance of y. That's what these first two terms are, expected value of x minus its mean squared, expected value of y minus its mean squared, variance of x plus variance of y. But unfortunately, we have some vestigial stuff. We have some stuff left over. In order for variance to split the sum apart like this, I need to argue that this stuff needs to be 0. Otherwise, up here, I would have the variance of the sum is the sum of the variances plus a whole bunch of other stuff. And that would not work out very nicely at all. So my claim is that stuff is 0 if x and y are independent, that we're really leaning heavily on the independence of those random variables. So what is stuff? What is the stuff that's being added on here? Well, it's twice this expected value. So if I can show that the expected value of x minus mu x times y minus mu y is 0, then I'll have done what I want to do. So that's my claim here. My claim is that the stuff is 0 if x and y are independent. Now we have to be very careful here. The expected value of a product is not the product of the expected value, so we don't want to go trying to use properties that aren't actually valid. But I do note that I have a binomial times a binomial, something with 2 terms times something with 2 terms, so I can FOIL these out, use the linearity of expected value. Expected values do break sums apart. Again, we've shown that before. And I have expected value of xy minus expected value of x times mu y minus mu x expected value of y, and then plus mu x mu y from multiplying this out and keeping in mind that mu x and mu y are constants. Constants can come out of expected values, and the expected value of a constant is just that constant. I note that expected value of x is just mu x. Expected value of y is just mu y, so I have minus mu x mu y minus another mu x mu y plus a mu x mu y. So net, I have just a minus mu x mu y. So my stuff that I want to show is 0 can also be written as expected value of xy minus mu x mu y. Or in other words, if I can show that expected value of xy is equal to mu x mu y when x and y are independent, that means that my stuff has to be 0, and that means that I can split my variance of the sum into the sum of the variances. So unfortunately, I don't know a better way to do this than to just kind of brute force it. So what's the expected value of the random variable xy? Well, we can be a little more explicit about what we mean here. The random variable x has certain outcomes. Let's call them x1 through xn. The random variable y has certain outcomes. Let's call them y1 through ym. So the expected value of the product of those random variables, well, the product of the random variables will look like products of their outcomes. So for instance, xy, the random variable, might sometimes be x1 times y1, the product of those two outcomes. When will it be x1 times y1? It'll be x1 times y1 when the random variable x equals x1 and also the random variable y equals y1. So we have the random variable xy has an outcome x1, y1 with probability that x equals x1 and y equals y1. And similarly, the product xy will be x2 times y1, and that'll occur with probability when x equals x2 and y equals y1, which I've just kind of concatenated to probability of x2 and y1, and so on down the line. Here's where we're leaning heavily on independence. While I have the probability of A and B, right? Two different events, x equals x1, y equals y1, that are connected with and I have a multiplication rule for independent events that says that I can split these probabilities apart, right? that this and in essence becomes a times. So I can split that using independence between x and y into probability x equals x1 times probability y equals y1. I can do the same for this one and this one and all of the rest. The independence between x and y is what lets me split the probability of A and B into probability of A times probability of B. Now what can I do? Well, now I note that let's take a look at line 1 here. I note that in line 1, every term has a factor of y1 and every term has a factor of probability of y1. I can factor those out of y1, or sorry, line 1. y1 probability of y1. What am I left with? I'm left with x1 probability of x1 plus x2 probability of x2 and so on out through xn probability of xn. So y1 probability of y1 factors out, and I'm left with the sum of the x's times their associated probabilities. I could do the same in line 2. I see that y2 probability of y2 factors out, and I'm left with exactly the same thing with the x's. And so on down to the line for the ym's. Ym, probability of ym factors out times this string with these x's in it. However, I notice that what is the sum of all of the outcomes xi times their associated probabilities? Well, that is just the expected value of x. Each of these bracket terms, or factors, I suppose, each of these bracketed factors, can't seem to select just this one, but each of these are just expected value of x. So I really note that what I have is y1 probability of y1 times this number that's expected value of x, plus y2 probability of y2 times this number that's expected value of x, and so on down the line. But now I realize that I have a sum of a bunch of things. I have a sum of m terms, each of which has a factor of expected value of x. That expected value of x can factor out. When I factor out that expected value of x, I'm left with y1 probability of y1 plus y2 probability of y2 plus and so on down to ym probability of ym. But wait, that's just the expected value of y. The sum of each of the outcomes of y multiplied by its associated probability. So this is just expected value of y times expected value of x, which is just mu x mu y. And since expected value of xy equals mu x mu y, their difference is 0. So this claim does hold, and therefore under independence, the stuff that we might think that we need to add at the end that would make this very messy ends up being 0 by independence. So we have now verified this step, that variances split sums apart if the random variables are independent. So it's quite often the case, this is just kind of a side note, it's quite often the case that the mathematical properties of variances are much nicer, and this is one of the big reasons why, that variances split sums apart. Unfortunately, variances have the practical problem that they're in square units. So if I tell you a number that's the variance, that I mean is some kind of descriptive statistic for the data set, it's probably going to be kind of confusing for you to interpret. So we like to report standard deviations when we want to give a descriptive statistic. But when we're doing mathematical analysis in the background, quite often we much rather have the variance to work with because it has nicer properties like this. Once we throw that square root in, that square root's a nonlinear operation. That just kind of throws a big wrench into everything. So it's a little bit kind of funny that when we're doing mathematical analysis, we like the variance, but when we're doing practical analysis, we like the standard deviation. We'll actually see that come up again in chapter 7 when we're developing a confidence interval for variance and standard deviation. There's kind of the thing that we would like to happen, but that doesn't really happen. And then there's the thing that does happen that's maybe kind of close enough. And then the very last thing is just kind of an interesting little detail. So up here, I said that we proved the weak law of large numbers. That would kind of suggest that maybe there's a strong law of large numbers, and there is. And the strong law of large numbers says, well, it basically says the exact same thing. It says that the sample mean goes to the population mean. So what's the difference? Well, the difference is in the type of convergence. So here's kind of just this is very much a side note. Actually, most of this document is a side note just to give you some of the theoretical underpinnings, but this is a little more of a side note. But if we look at a distribution like this one on the left here, that it has two outcomes, has outcome 0 or outcome n. Outcome 0 occurs with probability 1 minus 1 over n. Outcome n occurs with probability 1 over n. What's the mean for this distribution for any n, as long as n is positive? Well, the mean would be 0 times its probability, which is 0, plus n times this probability. N times 1 over n is 1. The mean for the distribution on the left is always 1. But what happens if I make n bigger and bigger and bigger? I get a larger and larger and larger right outlier, but it occurs with a probability that's lower and lower and lower. In the limit, as n goes to infinity, I have some really big number that occurs with 0 probability. So in the limit, this distribution on the left becomes just a distribution that is probability 1 of obtaining the outcome 0. In other words, we just get 0 all the time. What's the mean of the distribution on the left, where we just get 0 all the time? It's like a die with 6 sides that are all labeled 0. The mean is, of course, 0. It has one outcome, 0, times probability 1, the mean is 0. The distribution on the left converges to the one on the right, but the mean of the left distribution is 1, the mean of the right distribution is 0. Clearly, the means do not converge, even though the distributions do. That's kind of a very strange thing. And, welcome to mathematical statistics. Like, there's different modes of convergence. So this idea of convergence and distribution is a weaker type of convergence than some of the other convergence properties. So the strong law of large numbers has a different type of convergence than the weak law of large numbers. And the central limit theorem that we'll see in chapter 6 uses convergence and distribution. So it uses this kind of top type of convergence here, where we get some funny behavior where the distributions converge to one another, but in this kind of edge case, the means don't converge to one another.